going to introduce you now. Okay,
Sounds
hi
great.
everyone. Hi everyone. Welcome to the RMK Distinguished Lecture Series. It's a lecture series we established to celebrate the role of Dick Karp, who was the Simon Institute Finding Director, and not only the role in Simon's Institute, but most importantly, the role in theoretical computer science, formulating the central problems, contributing stunning results. And in that spirit, we feature visionary leaders in the field of theoretical computer science. And we're especially grateful today to have Toni Pitassi, our speaker. And Toni is a professor at the University of Toronto. I think she's a holder of the Bell Research Chair for now. And she's a member of the Vector Institute, where she also holds a CFAR AI chair. And she's also a visitor in IES, has been a visitor for the last 4 or 5 years. And her research is she's done so fundamental research in many areas, probably most well-known in complexity theories, specializing in proof complexity, communication complexity, but she's also done a lot of work on privacy, differential privacy, and algorithmic fairness. And she's had breakthrough papers in all of these fields, showing from lower bounds, mostly in the proof complexity area, to in what I would call an upper bound, that is defining models where you can achieve fairness, and protocols for fairness, say, and for differential privacy. And Toni's also a legendary mentor to postdocs, to students, and personal friend. And most important, her talk today is entitled, How Difficult It Is to Certify That a Random SAT Formula is Unsatisfiable. So please join me in welcoming Toni. Welcome.
Well, thank you. Thank you, Shafi. It's great to, can you hear me?
Yes.
Okay, it's great to be here. Particularly honored to be invited to the Richard Karp Distinguished Seminar Series. I was thinking about what I could talk about, and I actually do have one paper with Dick Karp, although we didn't know each other, or I didn't know, I knew of him, but I never met him, I think, when we had the paper. And I think it was a joint paper with Paul Beam and Mike Sachs and myself and Dick Karp. And I think it was either Mike or Paul that were talking to Dick. So anyways, I was lucky to have an early paper with him. And so I picked this topic. Albert Asseri suggested it, maybe not realizing that, but I picked this topic because it's something I've thought about way back, even in grad school when I was supervised by Steve Cook. And so for the special year on satisfiability and NP completeness, plus the Karp lecture, I thought this would be a good topic. It's an old topic. It's basically trying to understand how hard it is to prove that a random formula in the unsatisfiability regime, how hard it is to prove that. And I certainly don't own this topic, but I'm going to give you my perspective on it. So I can see some of you, and if anybody has any questions, you're free to interrupt me. I probably won't notice if you raise your hand, though, so just, I don't know, interrupt or Shafi.
Toni, they say that they cannot see you, but is there any need to see you? No.
Oh, you can't see me?
I can hear you.
I think so I can see myself. I have 2 screens on. One of them is you can see me on one of them, I think.
Okay, good. Let's keep going.
Okay, great. Okay, perfect. So just to start with basics, KSAT is a CNF formula. So it's a conjunction of clauses, and each clause consists of a disjunction of literals. Of course, the famous NP complete problem, and given such a formula, over say n variables, you want to output yes if it's satisfiable. In other words, if there's a Boolean 0-1 assignment to the variables that that satisfies or that evaluates the formula to 1 or to true, and you want to say unsat or 0 otherwise if every assignment falsifies the formula. And the question I want to talk about here is, so we're in that regime where the F is unsat, and we want to know how hard it is to prove or certify that such a formula is unsat. So to talk about this, we're going to take a little brief digression into proof complexity. So what is a proof? So informally, a proof is just, we think of a proof as like a graph where the input nodes, that's in purple. I don't know if you consider that purple or pink, but anyways, the input vertices, which are in this picture at the top, they're labeled with axioms or initial assertions, such as the clauses. So we're going to assume that all the clauses are true. There's an assignment that evaluates the true. We're assuming that for sake of contradiction. And then you have some set of rules that you can use to derive new formulas from previous formulas. And the goal is to finally derive the identically false or the empty formula. That's what a proof would look like if you're trying to refute an unsatisfiable formula. And if you're trying to prove a tautology, then the purple nodes will be labeled with formulas that are axioms that are always true, simple axioms. And then the bottom would be labeled with the tautology that you're trying to refute. Okay.
So, sorry, Tony, to interrupt.
Yeah, good.
But there's a technical issue here that the panelists are claiming that they cannot see your video, which is not good. So you need to switch.
Okay, I'm going to turn this whole thing off, and then we'll.
Tony, I think if you just unmute your other camera, the other source, and then use the audio from that one, and then mute the one you're currently using, the microphone you're currently using.
Okay.
Hopefully that'll help.
So I don't have that it's muted. It's not muted.
I don't think that you're connected to audio on the other camera.
Oh, okay, now they say they can see you.
Okay, I did nothing, so I'm not sure.
I don't know. Fine.
Okay.
No,
I don't know what happened.
if we chose the speaker view, we could see only the T. But if we choose the other image, we can see the video. This was it.
Ah, all right. So I was.
Is everybody good?
No problem.
Just keep
Yes,
going the way you were.
Thank you.
Sorry. Okay. Okay. Can everybody still see everything? Okay, I'll keep going unless I hear, but yeah, complaint if something's not. Okay, so here's an example. A resolution is one of the simplest proof procedures, and there's only one rule, the resolution rule, which is you can take two clauses. It operates on lines that are just clauses. So at the top here are all the clauses of the formula F that we're trying to refute. And the rule lets you take two clauses where one contains a variable and then the other one contains the negation of that variable. So like here, A or B and not B or C. B is the common variable that occurs in one positively and the other one negatively. And the rule allows you to derive the disjunction of all the remaining literals, removing the B from it. Okay, and that's a sound and complete rule. So if F is unsat, then there's always a sequence of applications of this one resolution rule that allows you to derive the empty clause. So this is a picture of a DAG associated with the resolution refutation of this formula. Okay. So that's intuitively what we think of as a proof, but it was formally defined as more abstractly by Cook and Reckhow in 1975. And their definition of an abstract or general proof system is a polytime function that takes strings onto the set of unsat CNF formulas. And the way you should think of this function as so for a proof system P, you think of the associated function A as taking as input a string W, where you think of W as an encoding of a P proof of some formula. And then A of W just verifies that it is a proof and returns the formula that it's proving. Okay. And you want that procedure A to be polynomial time. So you want to be able to verify that something's a proof in polynomial time. Okay. And what it's a proof of. And since this definition is so general, it's more or less the same as defining a proof system to be a feasible proof system to be an NP procedure for solving unsat. So the theorem is that there exists an abstract proof system where all unsat CNFs have polysize proof if and only if NP equals co-NP. Does that make sense? So this led to what's referred to as Cook's program, although I'm not sure this is what he had in mind at the time. But when the program is to basically build up techniques for proving lower bounds for stronger and stronger standard proof systems. And eventually, if we can prove lower bounds on every proof system, in other words, show for every abstract proof system, there's some sequence of unsat formulas that require super polynomial length proofs, then that implies NP not equal co-NP and also P not, and therefore P not equal NP as well. Okay. Okay. So this was defined in the early 70s, and since then, and even in their seminal original paper, they defined a whole bunch of types of proof systems, the most standard being the Phraga system, where the lines are formulas, and you have some fixed set of rules that allow you to derive new formulas from previous ones in some sound way. And this is sort of like a picture you see a lot of different proof systems and the hierarchy of them. So as you go up, they get stronger in the sense that if you have like TC0 Phraga with an arrow to AC0 Phraga, that means it can P-simulate the one below it. In other words, any formula that has a small AC0 refutation would also have a small TC0 Phraga refutation. So as you go up, the proof system has more expressive power, the rules are stronger, and so you can prove more things with shorter proofs. And so we're kind of like this boundary here. The green shows currently where we can prove super polynomial or exponential lower bounds, and above the green line, we're really, really stuck at the moment. So there's a second motivation for studying proof complexity and lower bounds in particular, which is even if you don't think this program is ever going to lead to showing that NP doesn't equal co-NP, it turns out that these proof systems are very natural, and even understanding a fixed proof system that's a general natural one like resolution or like Phraga, that tells you a whole lot about a large family of underlying algorithms for solving SAT. In particular, if you take a run of any complete algorithm for solving SAT, if you take a run of any complete algorithm for solving SAT and you run it on an unsat formula, the transcript of the run of the algorithm, you can view that as a proof of the unsatisfiability of the formula. And it turns out that even if you run a complete SAT algorithm on satisfiable formulas, depending on the proof system, sometimes that can yield insight sometimes in the process of doing that, running a SAT algorithm on a SAT instance, you would sometimes end up having to prove subformulas or related formulas are unsat in the process. So the bottom line is proving lower bounds on particular proof systems has a lot of applications to our understanding of large classes of related algorithms. And here's just some examples. This has been talked a lot about in the special semester. People in the audience are definitely more experts than I am on this, but resolution lower bounds, for example, proves that any resolution-based SAT algorithm requires exponential time in the worst case. And so CDCL is, very extremely important kind of family of algorithms that are used to solve SAT and run quite quickly in practice. Cutting planes is another example. That's a proof system. And so lower bounds for cutting planes proofs rules out a different family of algorithms that are based on this branch and cut procedure from optimization. And there's been a proliferation of results about the proof system sum of squares, where they're very tightly connected to a large family of semi-definite programs for solving exactly and approximating lots of NP hard problems. Also related to the extension complexity, which is another model of computation that's been used and studied extensively to solve NP hard problems. So the bottom line is that understanding the proof complexity of formulas in the system helps us to understand not unconditional lower bounds, but at least lower bounds for an important large family of algorithms. Everybody can hear me? Because I'm seeing some new things on the... Is there still a problem with hearing me?
Everybody can hear you. There's some issue about seeing you, but I think this is fine.
Okay.
Yeah, Tony, Tony, I'm sorry to interrupt. It's just that your camera's off on the device you're using to speak into. So if you want to keep it that way, it's fine. It's just we won't see you on the video. That's all.
Okay. Let's see if I can fix that. Yeah, I'm sorry. I don't know why it's off. It shows that it's on. So sorry about that. Okay. Okay, so some of the main questions that we ask in proof complexity, I'll just quickly, is we want to understand for a particular proof system, which formulas have poly-size refutations. And we're even interested in proving conditional lower bounds under some, not under the assumption NP not equal co-NP, but under a different conditional result, maybe an assumption about one-way functions or a crypto assumption or assumption about, either hardness of a function on average or worst case would be great. We're also interested in understanding the question of how hard is it to find or search for a proof in a particular proof system. That's called automatizability of the proof system. We also like to relate what I was just saying before. We want to relate proofs in this proof system to natural families of algorithms, so that understanding lower bounds on this proof system gives us, we can leverage that to prove lower bounds on limitations of exact and approximation algorithms that are based on P, the proof system P. And then we want to be able to compare the strength of the proof system P to other systems. Okay, so one thing that is a big problem for us, once you get to a reasonably strong proof system like a Phraga system, the Phraga system is just a very general system where the lines, think about that DAG that I drew, the lines or the circles are labeled with formulas. So a poly-sized proof, those lines would be labeled with polynomial sized formulas, and the number of formulas should be polynomial sized, and the rules are just sort of, there's many different ways you can axiomatize a Phraga system, but you can just pick some fixed set of, a finite fixed set of rule schemas that allows you to derive, any, that sounded complete. And one issue that we have, big issue that we have, is it's actually really hard to come up with formulas that are hard, in the sense that we think that, it's an infinite family of formulas, and that's unsatisfiable, but yet it's hard to prove them in, say, a Phraga system or bounded depth Phraga system. So what Sasha said in his survey article is awfully difficult to come up with even candidate hard tautologies. There's no such thing as tons of NP complete problems at our disposal. And the way I would say it is, we're in this conundrum where you have to be able to come up with a statement that you can express propositionally. So you can't just decide to write down, some really hard theorem in math that you think requires a hard proof. You have to be able to write it down propositionally. And for those types of statements that can be expressed propositionally, it tends to be the case that, number one, either they're true. In other words, that was supposed to be not true. So either they're not a tautology, so that rules them out, because then no proof system can prove them, or they are known to be tautology, or they're not known to be true or false. So a statement where we don't know if it's, for example, you could write down a statement that says that SAT doesn't have small circuits. So that's an example of a statement that we think is false, or we think is true, that it doesn't have small circuits, but we don't know. And so it's hard to even study the length of a proof of something when you don't have any insight into whether it's true or false or not. And then the third case is where we do have a system of formulas that we know is true, like the pigeonhole principle or something like that. But usually if we know it's true, there's a proof of it. And if there's a proof of it, there's a Phraga proof or extended Phraga proof. That's why those proof systems were defined, because they kind of capture almost everything that we know how to prove that's propositional. So we're in this bind where, like, we have a proof system that's strong enough pretty much to prove almost everything that we know to be true. But we're trying to prove lower bounds for it. So we have to come up with something that, that is still true, but that we can't formalize in the system. So that's sort of the conundrum that we're in. So a natural thing to do is to look at random distributions on random formulas. So random CNFs, everybody probably knows what they are. So we're going to denote script F delta NK to be the distribution of random formulas, where you pick delta times n clauses, each of length or each of width k. So each has k literals in them. And it's not hard to show using a union bound that for when delta is a sufficiently large constant, if you pick a random formula from this distribution, it'll be unset with high probability. And there's been a lot of beautiful work on this showing that this actually does have this sharp threshold. For every k, there is a sharp threshold value, delta sub k, I'm calling it delta k star, which for k equals 3 is roughly 4.267, where if you choose less than that many clauses, that special number delta 3 star times n many clauses, it'll almost certainly be satisfiable. But if you choose more than that many clauses, it'll almost certainly be unsat. So there's the sharp threshold happening at this value. And so the idea is, okay, well, let's just consider this distribution where delta is sufficiently large, so to the right of the red line. So in that regime, we know that the formula is almost certainly satisfiable, and we have an abundance of them, so that's good. And so now the goal would be to try to show or understand how hard these are to refute, okay? And so early on, back when I was in grad school, Bart Selman and Hector Levesque and some other people were really interested in this, and they sort of I think it's their work that spearheaded the thinking about these random formulas and how hard they are to refute. And so they did some kind of empirical experiments and showed that even though for k equals 3 in this picture, even though the threshold is at 4.267, that even if you pick many, many, many more clauses, I don't know, 1,000 n many clauses, you're way above the threshold. And if you look at standard resolution-based SAT algorithms for solving these instances way above the threshold, the runtime looked like it was, the runtime looked like it stayed really high for a long time. And so it seems like from the point of view of these resolution-based algorithms that passing this transition point is just completely unnoticed by resolution. So resolution somehow thinks even when we're so far above the threshold, that's consistent with the resolution. Resolution doesn't recognize that they're unsat now. And there's other families of random CNF formulas that you could study that have been studied that are super interesting as well. I just want to mention this briefly because I think they're just as interesting. They don't have quite the same long history, but they're just as interesting. So other random constraint satisfaction problems like random XOR or random KCSP, the planted clique or random cliques problem has been studied extensively, where you're picking the distribution is over a graph. So you pick a graph G from the Erdos-Renyi distribution, where you pick each edge to be in the graph with probability P, and for P a half, there's a threshold where the clique has size roughly log n, and that's so P equals a half is the threshold for cliques of size log n. And so people study, the formula corresponding to this graph, which is a formula that says that G has a clique of size, say, 2 log n. And we know, since there's a sharp threshold there, that's almost certainly, for almost all G, it's going to be unsatisfiable because the biggest clique will have size n. And so this is another example of a random family of formulas that are unsat, and how hard is it to prove them. The third one is interesting also for lots of reasons, that it gets to the meta mathematics of the P versus NP question. So now here you take a distribution where you pick a random Boolean function f. So that's a Boolean function on n variables. So to describe f is like 2 to the n bits. And so you pick f at random, and then hard sub f with the parameter s is a CNF formula that states that that f is computed by a size s circuit. And so for s being polynomial and g and f a random function, since almost all functions, are not computed by poly-size circuits, for a random function, hard f sub s and s polynomial hard f will be unsat. And again, the question is how hard it is to prove this, and this is kind of trying to understand how hard it is to prove the non-uniform version of P not equal NP. So I think these random families are super interesting to study. And one motivation is to study this, to study, they're interesting in their own right. Understanding them relates to structural properties of, NP hard optimization problems. And in the case of the last example I gave, it relates to our understanding of the P versus NP question. From a slightly more practical point of view, it gives a distribution of instances to use as benchmarks for SAT algorithms. As I mentioned before, like lower bounds for particular systems, and especially for these particular distributions of formulas, helps us to understand approximation algorithms for a large related family of algorithms. Okay, so why is it so hard? So now I'm going to just focus on the random unsat formula where we pick, M clauses where M is equal to delta n, where delta is bigger than the threshold. And so one question is, why does it seem so hard to certify that a random formula is unsat? We know that by a simple counting argument that they're almost all unsat. So why is it so hard to actually prove that a particular one is unsat? And one kind of obvious thing that is important is that there's a big difference here between circuit complexity and proof complexity. So in circuit complexity, it's easy to show that a random function requires big circuits because the number of functions on n variables is like 2 to the 2 to the n, and the number of poly-size circuits is more like 2 to the poly n. So there's way more functions than there are small circuits. And so that means that, almost all functions are hard. In proof complexity, we don't have the same, we can't do the same thing. So the number of proofs of size S is roughly proportional to the number of unsat formulas. So we can't just use a counting argument to say, well, we have all these formulas, so many formulas that are unsat relative to the number of short proofs. And then the second issue is, I guess I stole this name, truth versus proof, from Boaz Barak, which is that, the truth is we don't really know if these formulas, we're in this regime now where we don't know if it's true or not. So we know that most of them are unsat, that's true, but we don't know if they're hard to refute. And so back in '98, Paul and I wrote a survey, and where we said the only known lower bounds for random formulas are for resolution, and the absence of lower bounds for random set is quite noteworthy, especially given the lack of good upper bounds in any system, even extended Phraga. So the point is that we think they're hard, but we don't have any evidence really in either direction except for resolution bounds that I'll tell you about. And the really weird thing is that we have no upper bounds. So you would think, well, we do have some, but they're pretty trivial. I'll get to them in a minute. But you would think that, if you're a little bit above the threshold, or maybe, a large enough constant away from the threshold, that then somehow you could exploit the fact that they're so unsatisfiable that you could come up with a way to refute them. But that's not the case. And in fact, Feigus hypothesis is a formulation of exactly this question, of exactly this hypothesis that that there are no short proofs of any type for unsat formulas. So he defines he defines something called a refutation algorithm, which is just an algorithm that takes as input a formula from this random distribution above the threshold. And since almost all formulas are unsat above the threshold, you can't just say, well, the algorithm has to say, it has to get the right answer almost all the time, because then it could just say that they're all unsat and that'd be done. So instead you want to say that it has to output yes, where yes means it's unsat. It has to say that sufficiently often, say with probability half. So it has to get the right answer on a lot of the unsat formulas in the distribution. And anytime it's a rare one that's satisfiable, it always has to give the right answer. So it always has to say no. And he hypothesized that this is hard. There's no polytime refutation algorithm for F, and also that there's no proof system that has short refutations of a random F. And this has been extremely useful as a hypothesis. It's been shown certain problems that have been super stubborn in terms of proving anything about have been shown to be hard under Feigus conjecture. Certain approximation problems that have resisted proving that they're hard under normal NP hardness assumptions, and also other problems more of the meta-mathematical type, like the average case version of MCSP and famous result about pack learning DNF were shown to be connected to Feigus conjecture, and that if Feigus hypothesis is true, then these problems are also hard. Okay, so I wanted to say, I just wanted to make I just wanted to check on one thing. So is this, I should finish by 1 or before then? Sorry, 10 your time.
No, you can, it would be great if you leave some time for questions. So if you want to leave 5 minutes for questions, that's,
okay.
Yeah.
Okay, but it's 12 to 1, right? Or it's over it?
Yeah.
Okay, great. Okay, so let me just tell you a little bit about the upper bounds for random set. So this was the paper that with Dick Karp that I mentioned before, and I believe this upper bound, the idea was actually due to him. So the best we have for k equals 3. So when you're looking at random k set formulas, that you actually once you pick almost n squared clauses, then there are polynomial size resolution refutations, and more generally, n to the k roughly n to the k minus 1 clauses is what you need if you're doing random k set. So that's so far above the threshold, it's not even funny. Remember, there's only like n to the third many possible clauses. So we're extremely unsatisfiable. And for TC0 Phraga, which is a very strong subsystem of Phraga, of course that means it also holds for Phraga. These are upper bounds. So Phraga can refute random 3-sat formulas where the number of clauses is n to the 1.4. So it's better than resolution, but it's again, we're still super far away from the threshold. And this result was proved non-constructively by Feigus Hypothesis. It's a really interesting paper. And then it was shown by Muller and Samarat that you could formalize their upper bound in Phraga systems. And for lower bounds, so the picture almost looks the same as before I showed you a picture of lower bounds for proof systems where we could pick any formula we wanted. Here, this picture is lower bounds specifically for random set. And the only difference between the other green line and this one is AC0 Phraga, we don't have lower bounds for random sat, even though we do have lower bounds for AC0 Phraga for other formulas. And cutting planes, which is a relatively new result that I'll mention at the end of the talk, now we do have lower bounds. The dotted line runs through it because it's for K has to be at least log n, order log n. So we don't know the lower bounds if K is a constant for cutting planes. And again, everything in purple is hard, and that's what we're at right now. So here's a more detailed picture of some of the lower bounds that have been proven. So I'm going to first tell you a little bit about the resolution lower bound. It was originally proven. So the first lower bounds for resolution were due to general resolution bounds were due to Armin Haken. And that was followed up by a really lovely paper by Alistair Urquhart that used the same technique to prove lower bounds for a different distribution of hard formulas based on mod 2 counting. And then Kvatal and Samaretti in another breakthrough paper proved lower bounds for random sat above the threshold. And so they proved it when m is some sufficiently large constant times n. And then in the paper with Paul and Mike Sachs and Dick Karp, and also proven by Bensasun and Bigderson, we were able to push this up to the lower bound still holds even when the number of clauses is like n to the 1.5 for k equals 3. So I'm going to first tell you about that result, and then I'll briefly talk about the cutting planes lower bound as well. Okay, any questions so far? Okay.
My only question is that you use hard in different ways. So when you think about all those other things above the green line being hard, you mean it's hard to prove that they are hard?
Right. Good point. Right. So what I mean here is that above the green line, we have no idea whether say Phraga or TC0 Phraga has short proofs of random unsat formulas. So I don't care in general. We'd like to be able to prove lower bounds for anything for TC0 and up. We don't have lower bounds for any formulas at all. And the reason we're focused on random ones is because there's not many other choices. And so there I'd be happy to prove a lower bound is for random formulas where we're just slightly above the threshold, just so as long as they're unsat. Does that make sense? Yeah. And below the line, we do have proofs that random formulas are hard to refute for those proof systems. Does that make it more clear?
Yeah.
Okay, so I'm just going to give you first, I'm just going to try to explain a nice way to think about these resolution in the same, you can use the same way. There's going to be this, we're running through all of these lower bounds is the idea of thinking of a proof system as solving a search problem, a total search problem related to the unset formula. And the search problem is given an assignment to all the variables that underlie the formula, output some clause that's falsified by the assignment. So that's sort of, we want to kind of go from sort of a syntactic proof to some kind of semantic thinking about the proof so that we can use some combinatorial arguments to prove a lower bound. So this is going to be the function that we're going to be interested in. We're going to kind of study different proof systems and see that you can view different proof systems, proofs in those proof systems as sort of models of certain restricted types for solving the search problem. So the simplest example is tree resolution. So tree resolution is a resolution proofs with the property that they're tree-like, meaning that the intermediate clauses that you derive in the proof can only be used once. So if you want to use an intermediate clause more than once, you have to rederive it. So tree proofs in general are weaker than DAG-like proofs. And this is an observation that was made a long time ago. I'm not even sure who gets the credit for it, which is that tree resolution proofs are basically exactly the same as decision trees for solving the search problem. So if you have a tree resolution refutation of a formula, by looking at it slightly differently, it is a decision tree for solving the search problem, and vice versa. If you have a decision tree for the search problem, you can kind of think of it as a tree resolution proof. And here's just a proof by picture. On the left is a resolution proof. I flipped it now so that the clauses are at the bottom, and the empty clause, which is what we're eventually trying to derive, is at the top. And you can see it's a tree. It's not a tree in the sense that the leaf clauses, the clauses of F can be used more than once. So I could have just repeated them instead of making it look like it wasn't a tree, but it is a tree. And then the way you think about it as a decision tree is whatever variable you resolved on, that's what you label the vertex with. So for example, here, the clause x2 negated or x3 or x4 is resolved with x3 negated or x4. So x3 is the variable we're resolving on. So we label the corresponding parent vertex with the variable or the query x3. So we ask, what's the value of x3? And we do this for all of the resolution steps. We always just label the parent one with the variable that's resolved upon. And then the leaves are still labeled with the clause. And so that's a decision tree. And the leaves which are labeled with the clauses, those are the clauses that are violated by that partial assignment to that leaf. So in the right here, for example, when x4 is 1, that falsifies the clause x4 negated. And so that's the answer, and so on. Does that make sense to everybody?
Tony, this is Vijay here.
Yes, hi Vijay.
For the assignment 011.
Yes, did I make a mistake in my picture?
It
appears I did make a mistake in my picture, sorry. Yeah.
Oh, okay, okay.
Yeah, I think I just forgot to. Oh no, I think it's okay. Okay. Oh, it should be 10. It should be 100. I labeled them wrong. Yeah, sorry.
Okay. Yeah.
Yeah, sorry about that. Okay. So because of this connection, it's not hard to prove tree-like resolution bounds for random formulas. You just have to argue. So to argue that the proof has to be that the tree has to be deep. Let's do that first. That's just a matter of arguing, and it kind of follows by expansion. If you have a random formula and somebody asks you the value of a variable, you want to pick the direction or pick the setting of that variable that's going to leave the formula under that restriction still relatively hard. So by hard, I mean that you can't like locally find a contradiction. So you have to sort of look at lots of clauses to get the contradiction. And I'm not going to do this today, but it's not hard to come up with an adversary strategy that's based on the expansion of a random formula. By expansion of a random formula, I mean, if you look at the clause to variable bipartite graph, where you have clauses on vertices for the clauses on the left and vertices for variables on the right, and you put an edge between a clause and a variable, if that variable occurs in the clause, that graph is going to be very highly expanding in general. And because of that, there's going to be an adversary strategy that's going to force a path, no matter what the tree looks like, it's going to force a path of linear height. Now, what about for DAG-like resolution? So where it's not necessarily a tree. So we would like to come up with a model. We'd like to have a kind of a top-down view of DAG-like resolution proofs, the same way we had a top-down view of tree-like resolution. So you might think, well, the first thing, well, if tree-like corresponds to decision trees for solving the search, then DAG-like should correspond to branching programs for solving the search. And so I first just want to show you that that doesn't work. So it turns out that every unsat formula, the search problem associated with it has a linear size, a really small branching program for solving the search problem. And here's an example. The formula F here is unsat. And what the branching program does is you just query all of the variables in the first clause. So query x1 and we'll query x2. And there's a unique assignment to those variables that forces the clause to false, in this case, x1, 0, x2, 1. And so for that assignment, you're done. That's the leftmost one on the picture on the right. So you label that with the clause C1, which is falsified by that assignment. And now for all the other assignments for X1 and X2, you know that they satisfy this clause. So this is where we use the fact that the branching program is DAG-like. We can for all of those possibilities, we can just merge them all to a single vertex, which is the one shown on the right at the top. And then we can query the variables of clause 2. And so we keep doing this. And when we finally get to the second to the last clause, we query X2 and X3. And if they're both 0, then clause 3 is false. And now we know if they're not both 0, and so far now we know that none of C1, C2, C3 has been set to 0, then we know because F is unset that C4 must be unset. So we can just label the remaining paths by C4, even though we haven't actually gotten a witness to the fact that C4 is false. So this is bad news from the point of view of it is a branching program that solves the search problem, but it's not like a proof, or you wouldn't think of it, you don't really think of it as a proof, because you don't if you look at it, you don't, in the case of C4 being 0, you're not convinced that C4 is 0. Does that make sense to people? So Razborov, in 95, I'm not sure who gets the credit for this, but there is a way to think about resolution as a type of a branching program, but it has some more conditions on it. So it's a DAG, so it's like a branching program. It's a DAG where the vertices are all labeled. So each vertex is labeled with with a variable that you're querying, just like before. And one side is the variable 0, and the other side it's 1. And you also can remember at any vertex a subset of literals, which are literals that are, so you can think of it as remembering a partial assignment so far. And so it should be a partial assignment that's consistent with all the paths to that vertex. So if one path to a vertex set X1 to 0 and another path set X1 to 1, then you wouldn't remember X1 because it's not consistent. Whereas if you had a vertex where all the paths to that vertex queried X1 and set it to 1, then you could remember X1 as 1 if you wanted to, okay? And the soundness property that we need is that when you go down in this tree, that you're kind of, every assignment follows a unique path from the root to a leaf, and we want it to be the case that that the assignments that make it to a particular node, all of those assignments have to either make it to the left node or to the right node, or not, or both. And then at the bottom, at the leaf node, we want to label the leaf nodes, have to be labeled with clauses from the search problem, and those clauses have to include, so whatever is remembered at that leaf vertex, what the partial assignments is remembered, that partial assignment has to falsify a particular clause, and the particular clause that's labeling that leaf. Okay, so the proof that we showed before, where we said C4, even though the paths, all the paths to that vertex didn't falsify C4, that wouldn't be allowed anymore. Okay. So again, this is like a DAG. You should think of this as a DAG-like branching program for solving a total search problem, with the extra condition that it's not just solving it, it's sort of witnessing the solution at every leaf. Okay. And with this top-down view of resolution, we can proceed to prove resolution bounds. This is not how they were originally proven, but it's kind of the nicest way now that we think about it. We can think about resolution for lower bounds as proceeding by first showing that for a random F, any resolution DAG requires linear memory or linear width, meaning that there has to be, regardless of how big the DAG is, there has to be some vertex where we remember a partial assignment of linear size. Okay, and that sort of corresponds to in the tree resolution case, showing that any tree decision tree for solving the search problem has to have a long path. So this is the analog of that in the DAG case. We want to show that any resolution DAG for solving the search problem, somewhere along the line, you have to remember a whole lot about the partial assignment. And then we use this really lovely relationship by Ben-Sassoon-Vigdor that allows us to immediately go from lower bounds on width or memory to lower bounds on size. So their theorem states that any small size resolution DAG implies a width, so the resolution DAG has size S polynomial, then there's another resolution DAG of width square root of n log S, so roughly square root of n polylog n. And so that together gives us our contradiction. And the way we prove the width bound, part one, that's proven, again, by designing an adversary strategy similar to what I alluded to for the tree case. And the whole, what you're leveraging in the strategy is the expansion of the graph, meaning that you cannot locally, there's always a strategy where until you go for linearly, unless you're remembering a linear amount of stuff, it's not going to be possible to kind of know where the contradiction is without looking globally at a lot of clauses. Okay. Okay, so I'll skip. So this sort of this lower bound lets us know, or basically certifies this experimental results, that it really is the case that resolution-based algorithms for random CNFs, can't refute random CNFs even way above the threshold. And I wanted to mention one result that I think is really cool by Aklioptis, Beam, and Malloy, building on the lower bound techniques for random formulas. They showed something super interesting where they studied a class of algorithms for solving random instances of SAT that are based on resolution. But they were looking at SAT algorithms in the SAT regime. So random 3CNF formulas that are satisfiable. So where you pick, say 3n or 3.5n clauses. So the formula is almost certainly satisfiable. And what they were able to show using very similar techniques, but really great idea, is that when you're running one of these heuristics that are based on resolution on the random SAT formula, again, by leveraging the expansion properties of the formula, very likely it's going to be the case that even though the formula is satisfiable, before you find that good path, which is in purple here, you're going to stumble upon a sub-problem, which is the blue thing on the left. So you'll have fixed some variables, and you'll fix some partial assignment that'll leave you with a residual formula where you plug in that restriction. And that residual formula will be a mix of clauses of size 2 and 3, because you'll have set some variables. And that residual formula under this restriction will with very high probability be unsat and very hard to prove. So even though the formula is satisfiable, which is the purple Mick Jagger path, before you get to that, you're very likely to encounter a mixed formula, which is a residual formula that's unsat and that's hard to prove. So you're going to waste exponential amount of time refuting that before you move on to the nice purple line. Any questions? Okay, so cutting planes, I won't have time to say too much, but that's okay. I'm going to tell you what cutting planes is, state the result, and a little bit how the proof goes. So cutting planes is a stronger proof system than resolution. Lines are linear inequalities. So each line looks like, the sum of some constants AI, xi is greater than or equal to b, and those are called, the ai's and the b's are the weights. And the rules, standard rules for cutting planes is that you can take two previously derived inequalities and you can add them up. You can multiply previously derived inequality by an integer, and then the division rule, as long as you have some integer c that divides all of the weights on the left side, you can divide through by c, rounding up on the right. Okay, so this is the important rule, the third one, that kind of allows you to remove some non-integral points. So cutting planes have a fairly long history in terms of proving lower bounds. The original methods for proving lower bounds for cutting planes used a reduction to, so first of all, we look at very special types of formulas called interpolant formulas. So they're very special formulas of a particular type that allows us to convert a proof of a refutation of a formula of that type in cutting planes. Allows us to show that if you had a small refutation in cutting planes of this type, then you could kind of extract from the refutation a monotone circuit that solves a corresponding monotone problem. And in this case, we use a formula that's based on the clique. So a formula that states that a graph has a clique of size k and a k-1 co-clique, which is unsat. And then if you have a small cutting planes proof, it turns out that then you can extract from the proof a small monotone circuit that can distinguish graphs that contain cliques from graphs that contain k-1 co-cliques. And so then basically we're reducing the cutting planes lower bound to a monotone circuit bound. And that argument was generalized recently in a really nice paper that I won't say too much more about. But what is the problem for us? So if we want to prove cutting planes bound for random formulas, random formulas are not of this particular nice form that we were able to exploit in order to prove the lower bounds that I mentioned briefly on the previous page. But it turns out that we can still use the ideas behind that proof indirectly, because the random formulas kind of have so much, so many nice properties in they have so much embedded in them that when you look under the hood at the proof, you can kind of use the same properties, but more directly. So this theorem was proven by myself, Noah Fleming, Dennis Pankratoff, and Robert Ribeiro, independently by Pavel Hrubesch and Pavel Pudlak. Again, we showed that random log n CNFs above the threshold require exponential size cutting planes proofs. Yes, I'll just tell you in a couple of words about how the proof goes. So we're going to do the same thing we did before. We want to come up with a top-down view of a cutting planes proof. And the main thing that we want, the main point is that we want to still study the search problem, but now because the lines are more powerful, we want to study the search problem instead of studying the search problem in like a decision tree model or a DAG version of a decision tree model. We want to study the search problem in a communication model. And that'll be the analog of, we'll be able to think about cutting planes proofs of random formulas or of any formula as sort of solving the search problem via a particular type of communication protocol. So what do? Well, we have a random formula F. This is an example of one. Maybe it's not so random, but anyways, it has a bunch of clauses in it. Think of it as random. This is clauses here of size 6, but we're actually going to think of the clause that we're going to partition all the variables into two halves, into the blue ones and the red ones, and we'll call them X and Y. And for now, I'm just going to assume that the clauses of the random formula are actually roughly balanced. So every clause has like close to 3 blue variables and close to 3 red variables. And that has to be fixed up, and that takes more work. But this is still a random formula. It's just a slightly different model where you could think of it as picking one random formula, random 3 CNF formula with the blue variables, and then a separate one with the green variables, and then just put clause 1s together, clause 2s together, and so on. Okay. So this is the formula. Again, the only difference is that I've partitioned the variables into 2 groups. And for today, I'm making this assumption that all the clauses are balanced. It's the same search problem. Given an assignment to the variables, find a violated clause. But now we want to solve the search problem by a communication protocol where one player, Alice, gets the assignment to the blue variables. So we'll call that alpha. And another player, Bob, gets an assignment beta to the red variables. And they want to send bits back and forth now to agree on an answer, which is a clause that's falsified by F. So that's the communication model. And again, if we want a tree-like bound for cutting planes, then we can just study the normal communication complexity of solving this search problem. But if we want DAG-like cutting planes bounds, then we have to generalize the communication model to a DAG-like version. And that was done by Razborov. It's similar to what I said before. So that's the first step, but that was already done. And yeah, this takes some more work to do this for the case of cutting planes of big weights. But this is just a very high level right now. So the first thing we do is this general step of converting cutting planes refutations into showing that a cutting plane's refutation of small size gives rise to a DAG-like communication protocol for solving the search problem, communication protocol. And then the second step is to sort of realize that the DAG-like communication complexity of the search problem, you can kind of think of it in a different way, which is you can think of it as actually, instead of solving the search problem, you can think of it as being yes and no instances of a monotone Boolean function, where Alice gets a yes instance of a monotone function, Bob gets a no instance, and they're trying to communicate back and forth to find a variable where Alice's value is 1 and Bob's is 0. So that's the Karp-Wigderson communication problem associated with a monotone function. And it turns out that when you study the DAG-like communication complexity, the search problem is, or pretty much is, if you think about it the right way, the same as a DAG-like communication complexity of the monotone Karp-Wigderson game associated with a monotone function that's associated with f. We'll call that CSP sub f. And then it all basically boils down to proving monotone circuit lower bounds for this monotone function, the CSP sub f. So at the end of the day, we're extracting from a small cutting planes refutation a monotone circuit for solving this problem, very much like the interpolation method did, but we're kind of doing it in a less direct way. So at the end of the day, we're trying to prove a monotone circuit bound for CSP. And just to say a word about that.
Tony, I wonder.
I'm out of time. Yeah.
No, I wonder if you want to think like I mean, we are a minute out of time, but if you want to leave room for questions.
Yes, sure. Yeah, I'll skip that. Yeah, so I can just end here. I just wanted to say that I think there's a whole lot still to do here. Prove cutting, getting this lower bound hold for K being a constant is a really good problem. Like I said earlier, we really need some conditional bounds for Phraga systems. And a third one that maybe people don't think as much about is this whole area in logic, or called reverse mathematics, where instead of seeing what you can prove from theory, you instead take a statement that you care about and you see if you added that to a theory, or if you added that to a proof system, then what would the power of it be? So it's sort of like trying to understand how the relative strength of these formulas, in particular, like how strong a random unset form is. If you added them kind of as axioms to a weaker system like resolution or AC0 Phraga, could you then simulate a stronger system like Phraga? Is there some sense in which we can at least show that random unset formulas are ubiquitous? Yeah, that's about all.
Well,
so if anybody wants questions, and I can take.
I just want to say thank you for a fantastic talk. It's such a all-encompassing and so clear. So I just wanted to first of all.
Thanks. Good. Thanks, Sean.
Any questions? Quick question. Raise your hand or just unmute yourself. I think we'll digest.
I have a question. Albert here. So you mentioned here the circuit lower bound formulas, and you did state them earlier. And in fact, you did state a recent result that there's, if Feigus hypothesis is true, then the minimum circuit size problem is hard on average. And isn't that exactly a reduction from random set to circuit lower bound formulas?
Sorry, could you say the middle? You cut out in your middle sentence. So I heard you. Sorry.
Yeah. So you stated a recent result that says that the Feigus hypothesis implies that the minimum circuit size problem is hard on average.
I see what you're saying. Yeah. So I'm not sure. Yeah, I think you're right, but I'm not positive because I don't know how that result goes exactly. Are you familiar with it?
No, I wanted to know what you know about it.
Yeah, maybe we can talk offline. I don't know enough.
Okay, no problem.
Okay, so
yeah, but that is the kind of result I was that I think is really interesting.
So I think at this point, people should write to Tony separately and to ask her questions. And I want to thank you again for really wonderful talk. So thanks again.
Thanks, everybody.
Thank you, Tony. Bye-bye.
See you.